All right. And good morning, friends. We are here into week 4 and we are rolling. So it's going to be the end of, um, well, I don't know if the end is the right word, but the transitioning. So we're going to start transitioning into the second law, probably during today, or if not today, then definitely tomorrow. And it's a beautiful day here on the Central Coast. So I hope that wherever you are, it's also likewise sunny and not at all winter-like. So that's always a fun thing. In terms of what we have going this week, it should be PLC 4. As far as I know, it should be up and running and good to go in the usual format, the quiz style format. So that will go for Friday, and homework 2 is for tomorrow with quiz 2. And what else is going on? We'll have lab 4 coming up this Friday. Lab 3 would be due today then. So we've got PLC 4, and we'll go Friday on that. Homework 2 is tomorrow, and that is accompanied by a usual quiz. Lab 3 is due today, and Lab 4 will be on Friday as usual. So, other than that, I think that's basically it. So like I said, we've talked about first law, and we've talked about ideal gases, and we've talked about the ideal gas processes that we're going to go through, and we have talked about some of the atomic or molecular viewpoints that we can pull in here and talk about things like the internal energy being kinetic energy and the RMS speeds of the molecules and the mean free path, which I think we finished up with last time. And we're not going to delve too deeply much past that. What I'd like to do today is finish up a few things on kind of all of those subjects, kind of wrap those up, and then we're going to start transitioning into second law analysis and looking at what's going on with the second law. And we'll spend the rest of the time until the first celebration, which I believe is in about 2 weeks, I think. First celebration's in 2 weeks. So we'll spend most of the rest of our time looking at second law stuff and maybe a little bit of other fun stuff at the nearer to the end of that time period. All right, so left off last time with the mean free path and the idea that the distance between collisions for a gas was fairly large. All right, so our mean free path which is essentially, right, it's the distance between collisions. And this is on the average, okay? So we came up with an expression for that, and it looked more or less like, so I called it L, or you'll also find it named lambda in some textbooks. I don't particularly like that because that's a wavelength notation, so I'm not really going to use that. But we did end up with an expression that looks something like this, pi times d squared, and then pressure here, where the d squared is essentially the size of a molecule. It's the size of the gas particle, being that if two molecules of this, which are of the same species, are coming closer than a diameter, then we consider them to have basically hit each other. They had a collision. This would be the diameter of a molecule, or a gas particle, or whatever you might like to think of. Such that if I thought of something that was about like that, right? This distance here is d, which is just two of the radii, right? And so if their centers come closer than that, then we consider that to be a collision. Now, not that this is a super important expression, I tried to motivate it last time from the perspective of, well, what if we increased or decreased the pressure of the gas? Well, then we would have a difference in the mean free path. And the same thing with the temperature. Now, that's all fine and good. Excuse me. But what I think is really an interesting point here is that the mean free path in a gas and the mean free path in a liquid, right? So, for example, I took a jar of water and I thought about the water molecules in the liquid phase. And I thought about how far would they go before making a collision. Then I thought about the water molecules in the gas phase. How far would they go before making a collision? Even though these are both fluids, right? A liquid and gas are both fluids, but the mean free path is vastly different. All right. And I'll just tell you so that you have an idea of the difference here, in the sense that now, based on what I'm about to tell you, you see that a liquid is actually closer to a solid than it is to a gas. The mean free path in gases is approximately 10 times that mean free path in liquids. So if we have a liquid, for example, something that maybe it takes some liquid nitrogen or something like that, and then I have it in a beaker or something, I can measure the volume of this. And then I tip it out so that it's boiling, right? Because it will be easily boiling at room temperature. It's going to boil, and then I'm going to catch it in a bag or something like that. I'm going to say, okay, I'm going to seal it all off, and then I'm going to measure the volume of the bag, right? And so when I compare those two volumes, the volume it has in the liquid phase and the volume it has in the gas phase, you can imagine that this, when I have a small amount of the liquid of this stuff and I tip it out, it's gonna inflate maybe like a trash bag's worth. It's actually quite large, and that's giving you that you have about 10 times the mean free path, because the volume is about 1,000 times greater in the gas phase than it is in the liquid phase. So cube root of that would tell you that it's 10 times in each direction. So the mean free path is about 10 times bigger in the gas than it is in the liquid phase. Something to think about, because we really have tried to concentrate on independent gas particles moving around, and whatever they have going on, a liquid is way more complicated because they're so much closer and it's so much more dense. This is actually closer. This makes a liquid closer to a solid in terms of mean free path. Anyways, so we finished off with this. I just wanted to put that piece of info out there for your consideration and enjoyment. And other than that, I'm not too interested in lots more of this. This is mostly just helping you build a model of the ideal gas that we have been going along with. So to this point, let's see, we talked a little bit about adiabatic processes last time. I want to go back and do a little bit more of that just to kind of wrap things up and do a few other things about adiabatic processes. Well, I guess we'll do this first. I guess first we'll start with this. I'm going to go like this. This is going to be where you in the online class are at a disadvantage because you're not really going to be able to see this demo very well. But I'm going to show it to you anyway because, I'm just that nice of a person. We're talking about adiabatic processes, and I just want to revisit some of this. um, if we look at this on a PV diagram, right, this is the situation. What does adiabatic mean? Remember from our first homework set that the heat transfer is zero, right? Couple of key pieces about that. So in a problem, when you're reading the problem, you'll notice one of two things, most likely. Number one being a well insulated. You use the term well insulated as code for this is an adiabatic process. All right. So number one, either it's very well insulated, right? Or number two, and this is kind of related to one of the questions in problem set one, it's a rapid process. Something is maybe rapidly compressed or rapidly expanding or something like that where it's an adiabatic. So it's this idea of the rapidity of the process does not give the heat a chance to transfer. Therefore, in the problems, you're looking for these types of code words to let you know that, in fact, it's the heat that's going to not be able to have time to transfer, or it just can't because you have so much insulation, and hence we're talking adiabatic here. So before I go plot that on a PV here, well, actually, no, I am going to plot that. I'm going to do that first. So if I plot that on a PV. Typically, when drawing a PV diagram, and this is also good for review, the first thing I want to think about, it's blank, right? But I want to sketch in where are the isotherms, because we know for an ideal gas what they look like, and we should keep those in mind. So these things come in, right? Isotherms are kind of like something like this. Right? I'm going to think about isotherms as these reciprocal curves that are coming in like this. And that's not a great sketch, but it'll be close enough for it to work. Maybe even sneak one in down here. Right, like that. And the increasing in the temperature is that way. So lower temperature down here near the origin, higher temperature out here in the middle. Now the question is, where does an adiabatic curve fall on this? Well, an adiabatic curve looks like one of these, but not mathematically the same. So an isotherm and an adiabat are different from each other, and it's important. I still have seen, I know you folks are probably well above something like this, but I have seen a couple of instances in the other class where, remember, I tell people adiabatic means heat transfer to zero, not that the temperature did not change, right? So it's important to keep the isothermal and the adiabatic separate from each other. If I did, for example, an isothermal compression, what I would do is I would start down here and I would follow one of these all the way up, right? And my temperature would be constant the entire way. But if I'm going to do an adiabatic, what I'm going to do is I'm going to compress this, and maybe we can imagine that it's either well insulated or it's rapid enough. As I compress this, I don't let heat transfer out. That means that the temperature rises drastically inside the cylinder, the piston cylinder device, or whatever it is we have, such that I cross several of these isotherms as I compress it in an adiabatic process. So maybe my adiabatic might look something like this. It's definitely going to be much steeper, like that. Let me try and darken that in a little bit. So I'm going to cross several of these isotherms on my way from state to state here. How about something like that? Okay, so that'll be my 80 back. And therefore, since I've done that, you've noticed that I started on isotherm number 2 here, and I ended on isotherm number 5. So you can tell my temperature went up because I crossed isotherms going this way. Right? I went to one that was here, and then here, and then here, and that's the higher temperature one. Right? The work done by that process is still the area underneath the curve, and therefore you could drop this down here, drop that down there, and say, okay, it's all this area under here. That's all the work done by an adiabatic process. In this case, it's compression, and we're riding up the curve. If we're riding up the curve, it's an adiabatic compression, which means the volume is getting smaller, and therefore the temperature is increasing. The work is getting done on the gas. Were it to be an expansion, then it's riding that way, then it's riding out, and everything's awesome. Okay. Okay, so I have for you here this, let's see, I have for you here this. Okay, I'm going to hold this up for you. So this right here is let's see, I'm not sure if you can see. Oh, there, you can kind of see it. There's a small glass tube on the inside here, right in there, where this piston is. That's a piston right there. That piston is able to move inside that glass tube, and it's surrounded by this plastic outer. Now, the piston itself has rings on it, right? As pistons typically do, in order to stop any flow out around the piston and not so that it leaks, right? So we're trying to cut down on the leakage here. And at the very bottom of this thing, I've got a small piece of paper. So the question is, if I start the piston up here where this little band is, right there, then I compress it and I do it rapidly enough such that I don't give the gas time to transfer heat. So this is an approximately adiabatic process. This paper, now, if you're a fan of good science fiction, then you perhaps have read some Ray Bradbury, and then you would know the combustion temperature, at least in Fahrenheit, of paper, and that would be 451. And the question is, would I be able to get this gas that's in here, which is room temperature, and I think it's about 65 degrees Fahrenheit in here, would I be able to get it from 65 to 451, right, crossing these isotherms with a very quick adiabatic compression? In other words, could I get this thing to light on fire? So we're going to give it a try and see if we can do that. I'm not sure if we can or not. And ultimately, if we do, I don't think you'll be able to see it because your camera's, it might be so quick that the camera might miss it. So if it does happen, you'll hopefully see a little bit of an orange glow down here as the paper catches on fire, burns up, and then this tube will be filled with smoke. I don't know if it will show up on the camera very well at all. So what I'm going to do here is, I think I'm just going to put it about there, and I'm going to put the camera down a little bit so you can see this. So now, all right, let's try that again. Here we go. Now, okay, so here you can see that there, okay? And the piece of paper is all the way down at the very bottom here. So let's give it a try. I don't know if it'll work. And furthermore, I don't know if you'll be able to see it. So this might just be one where I go, yay, that's great. Sorry that you missed everything. And ultimately, we're going to move on. Sorry. Let's give it a try. All right, so I want to move, let's see, I want to leave that so you can see some dark background behind it. So maybe you can increase the chances of possibly seeing it. So if I hold it by the top here, I'm going to give this a good pounce so that I compress it rapidly, and let's see how we do. See if I turn it that way. All right. Okay, let's see how we do. Oh, got it on the second one. I saw a pretty good flame down there. I don't know if you did or not. Oh, good. All right. Let's see. It seems to be pretty burned up. I could try one more time just to see if we can get it to go. There's a little bit, no, there's a little bit more left over. There's a little bit more of a leftover there. That one was less impressive. I think the first one actually worked pretty good. Yeah, that was a little one. I think that paper is now burned up. Yeah, it smells like smoke in here. I've got a campfire in here, so we gotta somehow fish the dreads of that out. Anyway, so that's an adiabatic compression. Very rapid, right? As you can see, I'm pushing very quickly, and the piston is moving down. And I would guess that from here to there, I would say it's down here. That leaves a little bit of room at the bottom, so that's maybe, I mean, this is probably a compression of between 10 and 20 times. This is right, because if you look at I don't know if you can see the piston ring. So if I push it on the blackboard, maybe you can see, and I move my arm out of the way. You see those black rings right there? That's the end of the piston. So the volume is what's right here where my finger is. That's the leftover volume. In other words, that's the compressed volume. And I started the thing all the way back up here. So that's probably a compression of about 10 or 20, right? Therefore, what we're looking at is when I do this and I do it rapidly enough, I compress it by a factor of about 10 or 20, say, I don't know, in the middle, say 15. And we rise up those isotherms, which you currently cannot see, but you will again. We rise up the isotherms, and the temperature increases rapidly because we're not giving the time for the heat to transfer out. Now, that's the special case of an adiabatic, but then if I look at the special case of an isothermal, and I did want to do work as an isothermal process, how slowly must I be doing this in order to do an isothermal process? Right, I have to give a little bit of a push, and the gas goes, wait a sec, I'm compressed, I need to give off a little bit of heat. So you wait a little while that happens, and then you compress a little bit. You can see that this would take a much longer time to do an isothermal process. Now, maybe if I had it submerged in a water bath or something, that would help aid the heat flow more rapidly. But because heat transfer is generally a slow process, and as you know, radiation is the slowest of all. Whenever you're operating something in the way that we've been talking about, and I don't need to crouch down anymore, so I'm gonna stand back up here. The way we've been talking about things is that when I have this plot of the smooth curves on a PV diagram, this is an assumption that we've made that whenever we make a change to the system, right? So whenever I start here and then I go a little bit this way, we make a change to the system. I've done it in a way that is reversible, okay? So note that this is not a plot of what I just did because that was too fast. There was no equilibrium states in between. When I think about what I'm doing here is I'm doing this in a way that I could turn around and come right back. I'm doing it in a reversible sense. I'm waiting for everything to establish an equilibrium before I move on, right? The thing I just did was a completely non-equilibrium process. So we're not going to worry about trying to describe that mathematically too much, other than to note that I can actually describe an adiabatic process, so we'll do that now. And I talked a little bit about this, I think, last time, and we did a few things with it, but I'm just going to wrap this one up a little bit here. So let's take this out. And let's recall that in a process that's adiabatic, the thing that is constant is P times V, and V is raised to the gamma factor, right? And this is known as a constant. I never really understood what it meant when teachers wrote that on the board when I was a student, so let me make it a little bit more concrete for you. And let's go back to this. If I assume that we're doing a compression like we just did, then this would be state number 1 down here. And this could be state number 2 up here. And therefore, when I go from 1 to 2, I should be able to say that this and this are equal. That's what it means when I say PV to the gamma is a constant. That means you can pick anywhere else on the path. I could go here, 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 and I could say, I'm able to stop in the middle and do a PV to the gamma and find that it's the same all the way up. At least on this process, okay? Because this one was one in which we waited for equilibrium to establish at every point. And that's the assumption we're working on under in this class. Okay, so I have that as my adiabatic, that's my adiabatic condition. That mathematics got one of those adiabatic conditions. Should I go see the doctor? No, it's just that PV to the gamma is constant. And now we've got a gamma, which is Cp divided by Cv. And that's no big deal. It's the heat, the molar specific heat ratio. Let me just take another step back, and then we'll do a quick example of this. But let me take a step back and say that we know how to get both of these things. So, first of all, Cp is just equal to Cv plus R. Okay, for molar specific heats of gases, and Cv. We talked about this last time. Is just the number of degrees of freedom multiplying 1/2 times the gas constant. And for a monatomic, remember, that's 3. For a diatomic, that's 5. For anything else, if it's anything else above 5 would be polyatomic. You could imagine maybe 6 or, well, that's not true. Okay, hold on, that's not true. These are typical values. Well, okay, even that's not true. Okay, sorry, let me back up. This is always going to be monatomic, right? The diatomic could have 7. Now, this is a situation where, and I mentioned it briefly at the end or the middle or whatever it was, the end of the discussion we were having about this molar heats last time. I mentioned the vibrational states, okay? The vibrational states are even yet a step above the rotational states in a diatomic gas. So it could be, it's typically 5. It could be 7. All right, it could be 7 if the vibrational states are excited. Then anything that's not those is something even worse, like polyatomic or something like that. Now that's a 6 with no vibration. If it had vibration, then you probably want it's gonna. I'm thinking of like triangular molecule. You want to say I've got a 2 here, 2 here, and 2 here. That's 6. So I'm going to add 6 to that. It could be 12 pretty quickly. Well, not quickly, but it's not going to go to like 8 or 9 if it's a triangle molecule, right? If you're going to excite vibrational states, you're going to excite all of them. You're not going to. Well, that's not true, I guess. Gosh, I'm going to pull it not true. One of them might be a double bond on one side, might be a single bond on the other side. So it might be that this one's going to vibrate. These ones are going to vibrate a little differently. Okay, so I take that back. Maybe it can actually do that. Anyways, these are typical values, kind of rules of thumb. All right. Of course, monatomic is generally always true, but these two are dependent, right? So you have to make sure where you're at. So if you think about this in the sense of degrees of freedom, right? If I think about the gamma factor as the degree of freedom counter, then I'm gonna have basically F times 1/2 R plus R on the top divided by F times 1/2 R on the bottom. So really what we have, just get rid of all the R's because they are meaningless. Really what we have is F times 3/2 on the top divided by F times 1/2 on the bottom. And so I guess that means, is that right? No, that's wrong. That's wrong. See, I'm full of stuff that's wrong today. This is really F times 1/2 plus 1. That's F over F. You know, F over F. So that means that's really plus 2. No, that's true. That's true. It is 3/2, isn't it? 2, no. Yeah. 2, oops, I wanted 2 here. I wanted 2 here and 2 here. Yeah, so I was right. So this is F plus 2F. That's 3F over 2. Yeah, I was right. It's one of those days. 1/2. So this is going to go away. That's going to go away. So it's really 3 F over F. Oh, that's interesting. How did I get to that? 3F over F. So it's equal to 3. Okay, I don't really like this. Forget everything I just did. I did something wrong and I can't figure it out. Okay. Anyways, point being here that it can be a degree of freedom counter. Let me put it that way. It's a degree of freedom counter. So that if I think of a monatomic gas, and I think of what's gamma for a monatomic gas, then for a monatomic gas, I'd say this F is 3, and then I'm going to do 3/2 plus R, which is making 5 on the top. So this is making it equal to 5/3. And that's what I was getting at. I was showing you a little bit in the, I don't know if I showed you those tables last time, but we have tables of these values that are tabulated. So you can determine what structure the gas has from looking at the ratio of the molar specific heats. Okay. I'm going to follow up a little bit on the adiabatic piece here. Adiabatic is constant. Now, what if I took a step back and I thought about the other processes? What about an isothermal process? Well, an isothermal process is one in which P times V is equal to constant because the temperature is constant. So an isothermal would be PV equal to PV. Right? That's an isothermal because if you look at the ideal gas equation of state, nRT equals nRT because T2 equals T1, and therefore the PVs have to equal each other. If it's isobaric, then the pressure is constant, and if it's isovolumetric, the volume is constant, and also the work is 0. And so you get it. You can just go. But these two are the main basic ones. Don't get these confused. That gamma operates only on the V. It does not operate on the P. There are not parentheses here. Okay, so this is only on the V. Let's take a look at a quick example of this, and then I think I'll move into just summarizing a little bit more about the whole internal energy and kinetic energy thing, and we'll see where we're at from there. Okay, so let's suppose that our example, sorry, it's all ours. We can all have this one. We'll share. I have a gas. I don't know what it is. I don't know what structure it is. Okay, we're going to try and find that out. What I'm going to do is I'm going to let this gas undergo a free expansion. I haven't used that term in this class, I think, to this point. So let's talk a little bit about that. Let's have a gas undergoing free expansion. Into a container, and the container, say, increases the volume size, all right? So a gas undergoes free expansion. The gas initially has pressure of P naught. and it has a volume of V naught. And it's going to expand into a volume that's 3 times as big. So its final volume is 3 times bigger than its initial volume. How would you conceive of this? Let's draw a little picture of what this looks like. A free expansion is a situation where you have, and this is going to be 3 times as big, so I'm going to put it, say, here. Okay, so I have a container with a membrane here. Now the membrane is stopping all the gas. The gas is all contained out here on the left side. So we'll put the gas over here. Okay, so the gas is contained here. And what I'm going to do, and so here it's going to expand. Once I puncture this membrane and the gas expands, it's going to then be in a volume that's 3 times as big as it was before. Now, what is in here initially? And the answer is nothing, because it's a free expansion, meaning that it is unencumbered by having to move other things out of the way. The gas does not have to do any work in expanding. Okay? So what that means is, when I puncture this, these gas particles over here are free to roam around over here now. Right? Now in a free expansion, let's be careful about how we think about this, because anything that happens out into the atmosphere is not a free expansion, because if I have a compressed gas, kind of like I starting off with here, if I have a compressed gas and I let it expand into the atmosphere, well, it has to do work on the atmosphere in order to move the atmosphere out of the way so that it can take up some room in here. Okay, and this is why when you go to cocktail parties, and I hope at this point you are one of the stars of the show with all the stuff I've helped. I mean, for those of you who had me in other classes, we had this conversation. How to stand out at a cocktail party? Well, a lot of this stuff we can talk about. They opened champagne bottles. Now, champagne is compressed, right? There's a compressed gas in there, right? They have poured in some liquid, they've capped it off, and at some point, the carbon dioxide that was dissolved in the liquid some of it has come out into the gas form and is now occupying the little empty space, which is not empty. It's empty of liquid, but it's not of gas, right? And that's under heavy pressure, which is why they have to use those special necked corks for champagne bottles. Now, when you finally manage to work one of those out and it goes, right, and can shoot the cork, fun game to do at a cocktail party, although maybe don't aim it into the crowd. And you see, for example, the Europeans celebrate like this all the time. In the Formula One series, they pop the champagne corks and then start spraying the champagne all over everybody, and they're like, yay! Oh, great, now I'm soaked in champagne. Gross. And I have to go have a shower, which they don't have on site. You pop this open, but what do you notice? If you look carefully, what has happened is the gas in here has suddenly become cloudy, right? It's suddenly become very cloudy, and it has come cold, right? Or the same thing would happen with an aerosol or with a fire extinguisher. Anytime you have an expansion out into the atmosphere in which it's adiabatic, because it happened quickly, right? Like the reverse of this, the reverse of this thing, the compressor. If I have an expansion that happens quickly, then you find the opposite happens. That was a compression that happened quickly, and you saw the temperature went way up. This is an expansion that happens quickly, and therefore the temperature goes down. Why? Because it has to do work to move the air, the atmosphere, out of its way. This is not happening here. Sorry, that was a really long intro to that. This is not happening here. This is a vacuum on the right side of this, so it has no moving out to do. It will not do any work when I puncture the membrane. Right? This is a vacuum initially. So that there is no work done by the gas. If it's nice and insulated, maybe I'm going to put some insulation around this, then there's no heat transfer. And therefore, when I puncture this thing, there's no change in the internal energy by the first law. Okay? So suppose that I've got a nice layer of insulation around this thing. Okay, it's my insulation. And therefore, if it's insulated, we'd say Q is 0, right? If it's a vacuum initially, then there's nothing, it has to move out of the way, and therefore we'd say here that W is equal to 0. And you'd say, wait a minute, the volume increased. Well, yes, but there was nothing in its way, right? A lot of the times when we've talked about the volume increasing, we've talked about it has to push the environment out of the way. The piston is expanding, so you have to push the air out of the way, but there isn't anything here to do that. So in this case, the work is 0. And that's what free expansion means. I take these two things here, and I say, therefore, since I know what the first law tells me, since the internal energy change of the gas is Q plus W, and there wasn't either one of those, the internal energy of the gas has stayed constant. That means the temperature of the gas is the same. Therefore, delta T is 0, and this must be an isothermal process. All right. So this is a little bit of reasoning on this process, right? Free expansion. Okay, it's free, and that the free part means this, right? That it's expanding into nothing. It's free to expand. It didn't have to push something out of the way. We forget that the atmosphere is here because we're just in it all the time, so it becomes part of our daily knowledge or experience. So when you have nothing, then you go, oh, then I don't have to do any work. And therefore, free expansion is isothermal, which means that PV is constant, which is what I was just telling you a second ago. Or actually, I guess it's more than a second. All right, so for an isothermal process, then PV is a constant, so we'll call P naught V naught is equal to P1 V1. All right, so the gas now, I ruptured the membrane, right? Boom, there it goes, it's open, and now the gas starts to leak out and be over here. Okay, like this. Since it now has expanded into a 3 times bigger volume, what has happened to its pressure? Well, with all of the reasoning here, now it's easy to see. Think about, though, had I asked that question initially up here, you would say, well, I don't know, it's probably lower or bigger or high. It's the same. I don't know. Maybe it's isobatic. Well, now with all of this here, you can see what we need to do in order to find out what the pressure's done. Right? So looking for P1, you can see that it's going to be P naught times the volume ratio. V naught divided by 3 V naught. And therefore, this pressure is 1/3 what it was. Straight isothermal process. Right? Okay, now let's take the gas now and compress it back in to the volume that it had. Let's do that adiabatically. Okay, my next step after the free expansion is adiabatic compression. I'm going to try and stuff it all back into the original volume back over here. Adiabatic compression, it's done slowly, it's done reversibly, but I do have this layer of insulation out here, and so there's no heat transferred. Okay, for an adiabatic compression back to V naught, let's just start by doing a little plot of what this looks like. PV here. All right, so initially what happened was an isothermal expansion. So isothermal expansion, as we know, is going to happen like this. Right? That's my isothermal expansion. It's along a 1 over V curve. But now I want to adiabatically compress it back to the original volume. What is going to happen? What do I expect? Am I just going to go straight back up the curve? Well, no, because remember, adiabats and isotherms are different. The adiabat is steeper. Therefore, what I'm going to end up doing is when I compress it back to its original volume, it's going to go like this. It's going to be like that. Okay, so this one is going that way. I don't know, can you see enough? Yeah, okay. And this one's going this way. This is state 0. This will be state 1, and this will be state 2. Okay. Okay, so what do we expect from an adiabatic compression of the gas back to its original volume? What do we expect? The volume is going to be the same as it was. The pressure, well, that's not going to be the same as it was. That's going to be higher. The temperature, well, that's not going to be the same as it was. That's going to be higher. Okay? Yeah, so now I want to find out what are the properties here at state 2 compared to the state 0. Right? So let's take a look at this. And now since we know it's adiabatic, I know I can use PV to the gamma. All right, so let's do this. Let's do this. Let's do this. Yeah, that's gotta get rid of all this. All right. Okay. Now I'm going to take a look at the adiabatics process, and I'm going to say, all right, I'm going to look at P1. I'm going to look at P1 to P2. P1 V1 to the gamma equals P2 V2 to the gamma. Now, here's an interesting little piece. Suppose that we know what the final pressure is here at state 2. Suppose we know this pressure up here. If pressure 2 is equal to a multiple of pressure 0, so let's say it's something like the square root of 3 times big. Now, here's a kind of a funny question. If this is true, then we want to answer the question, what structure does this gas have? And what structure does the gas have is code. What is it code for? It's a structure of the gas. my question is, right? Is it monatomic, diatomic, something else, polyatomic? Yeah, essentially, right? Yes. How many degrees of freedom are there? What kind of gas is it? So we'd be able to actually know something about the molecular structure of the gas by doing an experiment like this and measuring the pressures. This is pretty amazing. Okay, so let's see if we can figure this out. If I know what P2 is, now I want to basically go up here and solve for gamma, right? That's the thing that's got all of that information contained in it. I need to solve for gamma. That's how I'm going to just determine this, because if I find that the gamma factor is 5/3, I'm going to go, oh, it's a monatomic gas. Or if it's something else, I'm going to have to figure out what it is. But I know for sure if it's 5/3, it's monatomic. All right, so let's solve for that. And from that, hopefully we'll be able to shed some light on what structure the gas is. Okay, so what I'm going to do is I'm going to kind of start plugging values into both sides of this thing. I've got P1, we know P1 in terms of P naught, right? P1 in terms of P naught was 1/3. So we had 1/3 of P naught. B1 is 3 V naught, and that's the gamma. And you say, oh, just real quick, I should just cancel those threes off, right? I can just cancel those. Can I? Because I've got 3 and a 1/3. I should just be. Remember, you've got this thing here, so that's everything in the parentheses. Okay, this is not 3 anymore, it's 3 to the gamma. So mind your basic math rules. P2, I've just been given that. Happy days. So square root of 3 P naught. That's going to come into the first power, and then V2 is the same as V naught. So I just have V naught to the gamma for the V2. Okay. So now let's try and prestidigitation. We'll see if we can't get the gamma factor out of here somehow. Well, what do we have? We've got the P naughts those can disappear because they are just to the first power in each one, so that can go away. Don't need that. What I'm going to end up with here is a 3 to the gamma, and it's got a 1/3 on the bottom. So basically what I have here is 3 to the gamma minus 1 times V naught, and that should equal square root of 3, but we know square root of 3 is 3 to the 1/2. 3 to the 1/2, and that is multiplying V naught to the gamma. Oops, forgot the gamma here on this thing. There we go. Okay, so I have 3 to the gamma minus 1 V naught to the gamma 3 to the 1/2 gamma naught to the V. Okay, by V naught to the gamma. All right, so now my gammas are contained really within the 3, right? Because these two things can go away with the V naught to the gammas are gone. Now I can just see that gamma minus 1 has to equal 1/2. And so from this, we'd see that gamma's 3/2. And you say, well, okay. Well, it's not 5/3. And it's not 7/5. And it's, well, it's 4/3. So it's getting closer. So this is probably somewhere in the polyatomic region, right? Is basically what this is getting at. So we have something that's not monatomic, that's not easily describable as monatomic. Yeah, see, this is kind of the thing. It's what do we know it isn't? Well, it's not monatomic.
it doesn't appear to be diatomic, and therefore it must be something else, right? And so you're just kind of left with okay, it's a polyatomic. So we know something about the structure of the gas now. It's at least something that's polyatomic. Now, look at this. If we had discovered that instead of being a square root, right? What if instead this was something like, uh, what if this was something like 3 to the 1/3? What if this was a cube root? Well, then I would have come down here and said this is a 1/3, and this would have been a 3, and then it would have been 1 1/3, and that's 4/3. That would have been a situation where if I had a gamma of 4/3, that's the same thing as 8/6. And basically, you can see that's definitely going to be monatomic because that's degrees of freedom of 6, because this works out as degrees of freedom on the bottom here. So that would have been 6, which tells you that it is a moving and rotating in 3 ways, but not necessarily vibrating, right? So this could be a polyatomic situation where it has 3 degrees of regular spatial freedom and 3 degrees of rotational freedom, right? If this was gamma, or sorry, if this was 3 to the 2/3, same thing would happen, right? I'd be able to say, oh, this is 2/3 here, 1 2/3. Oh, that's 5/3. I would have gotten a monatomic one, right? So it really depends on how the pressure, the ending pressure comes out. But what's interesting is that you can even think about doing this process and then finding out something about the structure of the gas itself, just from the knowing the final pressure after a free expansion and a adiabatic compression. And all of a sudden we can figure out the gas kind of structure, which is pretty funny. Okay, so solving for gamma, we found out something. It's polyatomic. It's probably doing something interesting. Let's take a look at what's the ratio of the, say, kinetic energies in state 2 versus what it was in state naught. In other words, basically, what's the temperature looking like, right? If we do that, let's just erase this. And let's take a look at that. So if I'm looking for ratio of kinetic energies, kinetic energy in state 2 to the kinetic energy in state 0, that should be something that's related to the temperatures, okay? So ultimately, the kinetic energy, and this was going to be something I was going to mention after this example anyway, so good timing. The kinetic energy is the internal energy of an ideal gas, right? There is no other internal energy of an ideal gas. It's all kinetic. Which means that when we think of the temperature is a thing that tells us that the kinetic energy is changing, right? If I have a delta T, I'm going to have a delta in the kinetic energy, and then therefore I'm going to have a delta in the internal energy. So what I've really got here is internal energy over internal energy, and internal energy is expressible as N times, well, let's do it the better way. It's F times 1/2 nRT, right? So it's F times 1/2 nRT. Now I'm going to take a look at the ratio of these two things, and I'm going to say basically whatever the degrees of freedom number is, that's the same. Mole number is the same. R is the same. The half is gone. Really, this is just a ratio of temperatures. This thing right here is therefore T2 divided by T1. Okay, so it's more code language. Okay, more code language where you're saying, oh, what's the ratio of kinetic energies? Well, okay. Let's find what's, oh, sorry, T naught. See, what do I pay you people for? Keep messing up and you keep sitting there being silent, saying nothing. Come on now. T naught I can find because I know P and V in that state. And T2 I should be able to find in terms of P2 V2 divided by NR. And I can ignore the NR because it doesn't matter, right? It's not really it's not really something that's it's going to get canceled. That's what I'm saying. It's going to get canceled. So it's really P2 times V2, and P2 V2 we know V2 is the same as V naught, and P2 is a root 3 times P naught. So this is going to be root 3 times P naught times V naught divided by NR. Yes, divided by NR. And now if I look at T naught, that's just going to be P naught V naught and NR here. So dividing these two is just going to leave me as a square root of 3, right? In other words, it's about 1.7 times as big. So if you know, if this is 100 Kelvin or 200 Kelvin or 300 Kelvin or whatever, you're just going to go 1.7 times that big, which does end up getting big. Well, it does end up being significantly larger, right? So it's if you're at 200 Kelvin, then you're going to go up to 340, and that's a big difference, right? That's from minus 100 centigrade to over that's way over room temperature, right? So that's what 70 centigrades. So that's a big change. Remembering that we are bound to use the absolute temperature in these cases, not the centigrade temperature. Okay, so this is a ratio of absolute temperatures, not centigrade temperatures. Okay, all right. Good times. A little bit of free expansion, a little bit of adiabatic compression, a little bit of prestidigitation, and we figured out some stuff about the gas. All right, pretty cool. I want to summarize up. Let's see, we've got about 10 minutes. So let me summarize up kind of the state of things so far. Let me summarize the state of things so far. Um, it it can get I don't want to say it can get overwhelming, but it can get to be kind of a lot of stuff, especially because we have to kind of necessarily look at equations a lot more than I really want to focus on. But unfortunately, this is kind of the basis of the class. So let's take a look at what's been mostly important to this point. I'm going to start with the recent stuff, and then we can kind of morph back into the older stuff. So some of the high points, what's important? Looking at the ideal gas processes. Okay. What I'm gonna say, first of all, what's important is the first law. Right? This is so far top of the mountain for us. This is the big thing. Now remember, we are applying the ideal gas as a backdrop to study the thermodynamics of the situation. And I've said that since week 1, that we want to take the thermodynamics that we're learning and apply it to an ideal gas because it has a simple equation of state. It's a basic, easy system to understand so that you don't have to get wrapped up in trying to figure out how does this equation of state work with all of this stuff, right? We can just hopefully learn the thermo. So this is the big thing. This is the first law. All right. So tomorrow, that means we'll start on the second law, which will be great. In terms of ideal gas stuff, okay, there's a lot of pieces that come out of looking at the ideal gas. Okay, the ideal gas tells us that PV equals nRT, which you probably are tired of hearing at this point. And I wouldn't blame you too much if you were. Nonetheless, we have to work with it. So that tells us this. Because of the ideal gas and the first law, we have 4 basic processes that we wanted to study. One in which the pressure was constant, one in which the temperature was constant, one in which there was no work done, and one in which there was no heat transferred. Those are the 4, right? It's P, Q, W. right? That's the way I think about it. So looking at the four processes that we want to study, one of constant P, one of constant T, one of Q equals 0, and one of W equals 0. Of course, this also means constant V. Okay. So you can also look at it that way. Well, hold everything in there, at least one thing constant in the ideal gas equation of state. So I think in general, these come out fairly easily to consider. The work, we went with integral of PdV. And that's just the area under the curve. We came up with an expression for the work in an isobaric. We came up with an expression for the work in an isothermal. I mean, you can come up with the expression for the work in an adiabatic, but there's almost no point, because if it's adiabatic, this is already gone, and therefore the work and the internal energy change are the same thing. So if you can find the internal energy change, you know how much work was done. So essentially, there's no reason to really try and integrate the curve to find the work done underneath it. Typically, you just use the internal energy change. Okay. In the first law, we talked about how to find the work. We talked about specific and latent heats. And those two I want to be real careful with, because I feel like if you have a big chemistry background, of course, the thing you have to do is really start unlearning a lot of that because it's not useful. So because I think that chemistry teaches you that Q equals MC delta T is like this huge thing, right? It's not. It's not. Does it have its place? Certainly. Yeah, when it's talking about calorimetry and there's a sensible heat transfer and the states aren't changing. Sure, very important. That's great. But that's not always true. We have to be more careful. We are discerners. Okay, we discern when is it appropriate to use something like Q equals MC delta T or its molar specific heat form, Q equal to NCV delta T or NCP delta T. When can we use those? We can only use them according to the subscripts. If this is a constant volume process, there is no work being done. There is only heat transferring. Therefore, the internal energy change follows this. If this is a constant pressure process, isobaric, then the heat transferred is this. There is work being done. Nonetheless, this is how you calculate the heat transfer. Well, what if it's an isothermal process? Or what if it's an adiabatic process? Then you can't use those because those are not constant volume or pressure processes. So don't try to, okay? Right? These come right out of MC delta T. And you say, well, if it's an adiabatic, can't I just use MC delta T? No, you can't use that. What you can do, though, is you can look at the first law. So we go back to the first law and we say, okay, what do we have? What we have here for an internal energy change for the ideal gas is that this is always true for the ideal gas, right? It's F times 1/2 NR delta T. I'm going to get the delta in there this time. Where this F is the number of degrees of freedom the gas has. All right. Now, this is always true for an ideal gas. This is the internal energy change of an ideal gas. That can be used here. But these are not always true for Q. Okay. This is always true for W. It's always this. It's the pressure, it's the area under the pressure volume graph, right? This is true. This is the definition of the work. This is, in our model of the ideal gas, how we reference the internal energy of an ideal gas. That means that if the process is not one in which I can say it's constant volume or constant pressure, then I can't use these to find the heat transferred. I have to go back to the first law to do that. Okay, so that's that piece. Um, the other thing to go back to here, and I will say that are there lots of equations that have come out of this? Sure. But you know what? They're easily gotten. So I'm not going to go back and apply this equation of state to all of these to show you, oh, it's got to be this, it's got to be that, it's got to be the other. You can find all of those. That's easy enough. The important things are the first law, the equation of state, kind of having this idea of what the processes are, and then knowing you can hold this in you can hold this in high regard for an ideal gas. This is true. It's funny because it looks a lot like this for the heat. And you say, oh, well, that's the same as the heat transfer. Well, you just have to be careful about how you're using these things. All right. This is true for the internal energy of an ideal gas. The last things we did were things like oh wait, we did heat transfer. We did heat transfer. So let me just do a little bit on that here. We did do some heat transfer. So that meant that we did conduction, convection, and radiation. And those I justified them reasonably, but ultimately we ended up with conduction. Let's say the power of conduction being equal to the conductivity, the area, the difference in temperature. Let me just write those out. So for example, the hot minus the cold. And this whole thing divided by the thickness or the length or the whatever the size of the thing that the heat has to transfer through. When we did radiation, we did the uh, we did the the emissivity, the black body. How much of a black body is it? We did the Stefan constant, the surface area, and T to the fourth in kelvins. And then for the convection, we didn't really do a power of convection. We just did more of a how is the temperature changing? And it's changing via, well, we mostly concentrated on the delta T. So let's do this of delta T is equal to T, T naught, or no, sorry, T minus T environment. That with a K in front of it and a minus. So the difference in temperature between a hot object and an environment, a surrounding environment. That difference in temperature is related to that difference in temperature. Or I should say, the rate of change of that difference in temperature is related to that difference in temperature. And so those are the three heat transfer methods we looked at. And then the last thing to know is the Boltzmann or the Maxwell-Boltzmann distribution. Remember, I was not talking about the mathematics of this, but more the physics of what the shape of the distribution was. We did talk about the VRMS. We did talk about the VRMS in the context of what might be considered as an average, the RMS speed, and then the relationship of that to what's going on with the tail, the high speed things at the very tail of the thing. So it's nice to know, it's nice to have the Maxwell-Boltzmann distribution in your mind as kind of a helping guide to some physical reasoning. So for me, those are the high points. What we'll do is, since we have to stop, what we'll do is we'll pick up in the second law starting tomorrow. And quiz, I'll open up for your enjoyment tomorrow. Please be sure to have the homework submitted. Quiz will be available until midnight, as usual, a 1 hour, and make sure that you don't leave yourself too little time to finish off, right? Don't start at 11:45. and hope that you can get finished with it because you still have upload, download time, all that stuff. All right. Okay, great. Thanks again for your attention, and I will hopefully see you tomorrow. Happy day, folks.